The last topic that we will look at in section 3.2 will be on graphing polynomial functions. And when we graph polynomial functions, we're really going to put together all the individual concepts we've looked at so far in the chapter as part of our graphing procedure. If you refer to the graphing functions handout posted on Blackboard, of course we're focusing here on our procedure for polynomial functions, but I will connect to some of the procedures and steps we saw for quadratic functions. There are some similarities. For instance, with quadratic functions in step 1, we were really determining the basic behavior of the graph, right? If that leading coefficient a was positive, the parabola opened upward. If it was negative, it opened downward. Well, step 1 is very similar. We're going to determine the end behavior using the leading coefficient test for that leading term. All right? And two steps that are also similar will be finding the x-intercept and the y-intercept. We did that with our quadratic functions. Now, one thing I do want to note, in step 2 with quadratic functions, we can use this general form vertex formula to find the vertex. Do not apply the vertex formula to polynomial functions. Right? It does not apply. Only use this formula for quadratic functions. Do not use it for polynomials. There is no vertex for polynomials. Now, just remember, for polynomial functions, besides finding the x-intercepts, we do want to look at the multiplicity of those zeros to identify whether the graph touches and churns at an x-intercept or crosses the x-axis. So there's an extra piece of information there that we will have when we're graphing polynomial functions. And then steps 4 and 5. Step 4 was symmetry. This is usually most useful if you have even or y-axis symmetry. Sometimes you can have origin symmetry. Very often you will have neither. So the symmetry step maybe not quite as important in all problems as some of the other steps. In step 5, we'll use our turning points formula to evaluate if our graph is drawn properly. We can identify the maximum number of turning points as n-1. And I've added an additional step that you won't see in the textbook. But sometimes after we put together all the other pieces of our graphing procedure, we like to plot a few additional points just to confirm the graph's characteristics or shape. Let's look at example 9 from page 374 of your textbook. So they give us this polynomial function, f of x is x to the 4th minus 2x squared plus 1. Our first step would be to determine the end behavior. The leading coefficient a sub n is 1, so that's greater than 0 or positive, and the degree is 4, that's an even number. So in this case, our polynomial is going to rise left and rise right. In step 2, we want to find the x-intercepts, so we'll set our function f of x equal to 0. So we'll set this equal to 0, and you can actually factor this function as x squared minus 1 times x squared minus 1 equals 0. Now, x squared minus 1 can be factored into x plus 1, x minus 1, and that will happen twice. So then we can actually rewrite it like this. Now, solving for the two roots, we will get that x equals plus or minus 1. And if we look at the multiplicity of our factors, k equals 2, that's even. So what we can determine here is that the graph will touch and churn at each of those x-intercepts. So we can say the graph touches and churns at minus 1, 0 and 1, 0. In step 3, we'll find the y-intercept, which in this case, just like with the quadratic function, we'll just substitute x equals 0 into our equation. And so, of course, these two terms will go away. We're left with the value of 1. And again, I want to put that in coordinate point form so we can graph. So we'll have the point 0, 1. In step 4, we'll try to use symmetry to help us graph the function. So we want to evaluate f of x at minus x. So of course, where we see x, we'll substitute minus x in each of those terms. And so when we evaluate, because we have even exponents with both of these terms, this will evaluate to x to the 4th minus 2x squared plus 1, because this expression equals our original function, this means that we have even or y-axis symmetry. And in this case, this is usually when the symmetry step is most helpful, because you know that your final graph will have to have a mirror image type of symmetry around the y-axis if you've done it correctly. Very often in some problems, the symmetry step really isn't helpful, but when you have even or y-axis symmetry, it can be quite useful. In step 5, we'll look at the maximum number of turning points the graph could have. Because this is a 4th degree polynomial, n is 4, so our maximum number of turning points will be 4 minus 1, or 3. Now that we've gone through all the steps, let's put together all the information boxed in red here to draw the graph. We know the graph will rise left and rise right. So generically, we know the shape will be something like this initially, based on that first step. Now, we also know from the intercepts, the graph touches and turns at minus 1, 0 and 1, 0. So we have an intercept here and an intercept here, and the y-intercept is at 0, 1. And so we know because of the touching and turning, the graph will come down, it will go like this, and come down here. We know we have even and y-axis symmetry, so we see that symmetry here on the graphing grid around the y-axis. And the maximum number of turning points is 3, which we have 1, 2, 3 turning points. I have included a step 6 in our graphing procedure, which I call other points, which in some problems you can just confirm the graph shape by sometimes substituting key values into the function just to confirm the picture or fill it in. So we have these intercepts at minus 1, 0, and 1. So I'll just substitute the value of x equals 2 and minus 2 to confirm the behavior on those ends of the graph. And when you substitute x is 2, you'll get a value of 9. And minus 2, you'll also get a value of 9, which makes sense due to, of course, the fact that it has even or y-axis symmetry. Now that I've calculated those two other points, here's a little more accurate version of our graph, with now you see those extra points just to confirm the behavior on the graph on the left side and the right side, and of course the intercepts we determined from the earlier steps. Now, do pencil problem 8. Let's look at one more example of graphing a polynomial function. And this is example 10 on page 375 of the text. So here, f of x is given to us in factored form, which looks a little different from example 9. One nice thing about the factored form is that you can identify the zeros or x-intercepts and their multiplicities very easily. But we'll still go through the same 6-step process we have when we graph polynomials. Step 1, determining end behavior. The leading coefficient will be negative, and remember when we looked at the leading coefficient test earlier in the chapter, when you have it in factored form, we really need to look at the degree of each factor. So the degree of this polynomial, we'll get a degree of 2 from this term and a degree of 1. 2 plus 1 is 3. So negative leading coefficient and odd will have opposite behavior. That will be rise left and fall right. Now, because it's in factored form, finding the x-intercepts is actually a bit easier. So our first factor, x minus 1 squared, the root is x equals 1, but the multiplicity is 2, which is even. So the graph touches and turns at 1, 0. In this factor, x plus 2, the root is minus 2, but k is 1, which is an odd multiplicity. It will be crossing the x-axis at minus 2, 0. Step 3, find the y-intercept. We substitute 0 into our equation here, and eventually you'll get a value of 4, so the y-intercept is now 0 and minus 4. In step 4, sometimes we'll use symmetry to help us graph the polynomial function. But I mentioned in our example 9 that sometimes this step isn't very helpful. It's most helpful if you can identify even or y-axis symmetry, but very often you will get a symmetry of neither, which doesn't help you much with the graph. And if you look in the textbook, for this step, instead of multiplying these terms out and getting f of x in a non-factored form and then evaluating it at minus x, One thing you can do is if you do some initial graphing, that can identify whether you have any symmetry. So remember, we know generically our graph rises left and falls right. And we also know that the graph is going to touch and churn at this point and cross the x-axis here at this intercept. And so we can guess that the graph is going to then come down here and go through the y-intercept. So if you look at this picture, it certainly doesn't have y-axis or even symmetry, and it doesn't have origin symmetry. So from initial graphing, all right, we can say, I'll just write initial graphing, we can identify the symmetry as neither. In step 5, we'll look at the maximum turning points. And since the degree of the polynomial is 3, then of course we have 3 minus 1 or 2 maximum number of turning points. Now that we've gone through all 5 steps, let's try to complete the graph. So we've done our initial graphing and we determined that we have no symmetry here. And we know now from step 5 that we have 2 possible maximum number turning points. So it looks like the graph is going to come here, and this must be probably another turning point somewhere in here. Now the step 6 I've added other points is just to be intelligent about picking a couple key coordinate points to substitute into the function to confirm the graph's behavior. So I'm going to pick the point x equals minus 3 just to confirm this rise left behavior here on the graph. And I'm going to pick the x value minus 1 to confirm what's happening in the graph in this space here. And then I'm going to pick an x value of 2 to confirm this falling right behavior on that part of the graph. So I'm going to be very precise and smart about which points I'm going to pick just to fill in the picture to complete the graph. So to calculate these other points, I'll take these x values and substitute them into the equation of the polynomial function and evaluate carefully. So when x is minus 3, we get this coordinate point minus 3 and 32. When x is minus 1, we'll get this coordinate point minus 1, minus 8. And when x is 2, we'll get this point 2 and minus 8. So now what we can do is really complete this graph, make it look a little bit more accurate, and we'll be done. So let me plot these points. This point here will be 2 minus 8. And then we have this other coordinate point, minus 1, minus 8. And the point 3, minus 3, 32, I really can't plot to scale, but we can sort of just draw it here, and it will confirm the behavior of the graph. So again, this is what the graph will look like when we put all the pieces together. So this is a good example of graphing a polynomial function when it's given to you in factored form. Just be careful with the leading coefficient tests in the first step, but finding the x-intercepts and identifying their multiplicity should be a little more straightforward. And again, here we've filled in all the parts of the graph, right? We know it crosses the x-axis at this intercept. Here's our y-intercept. It touches and churns at this intercept. We knew it rises left, falls right. All those pieces we put together to come up with the final graph.